In the last video, we talked about what is integration by part techniques and where it's coming from, and some of the easier tricks to start with any problem. So here in this video, we're going to focusing on the examples. So the first one we have is we want to find the antiderivative or integrate ln of x dx. We only have one function, which is ln of x. However, we do not know what is the antiderivative of ln of x. In other words, we do not know what kind of function when you take the derivative is equal to ln of x. And that's simple. So the best way to figure out this one is to using integration by parts. Then you probably ask, I know integration by part, we need to choose u and the dv. For the u, we need to take the derivative. For the dv, we're going to take the antiderivative. But either way, we need to have two terms, two functions doing multiplication. But here we only have one function, which is ln of x. What is the other function? The other function is actually dx with invisible 1. So 1 times dx is the other function if you cannot find any other second function. So we're going to let u equals to ln of x. Let me move it to here. Then du is equals to 1 over x dx. dv is going to be 1 times dx. Then the integration of dx, or the 1, is just x. Then according to the formula, that integrating of u dv is equals to uv minus integrating v du. So what we have is going to be u times v, which is x times ln of x, u and v, minus the integration of the u dv, v du, which is those two, x times 1 over x dx. X times 1 over x, we know that is 1. And we also know the integrating of dx, or 1 dx, is just equals to x. And plus c. And this is our answer for this antiderivative. Now let's look at another example. This time we have two formulas, two functions, x and the ln of x. According to our trick, that we should let u equals to ln of x, du is equal to 1 over x dx. We should let dv equal to x dx. According to the power rule, the integration of x dx is going to be 1/2 x squared dx. No more dx. 1/2 x squared. Then, using the integration by parts, which is uv 1/2 x squared times ln of x minus integration of the v du, 1/2 x squared multiplied by 1 over x dx, which is something we can simplify. Move out the 1/2 to the front, x dx, and we also know when we just did it, the antiderivative of x dx, which is going to be another 1/2 x squared. So the final answer we got is 1/2 x squared ln of x minus 1/4 x squared plus 2. So quick note, this 1/2 is coming from this 1/2, so it's here. But this 1/2 is coming from this portion. So let me just using some underlines to denote it. So that is why we have two 1/2 multiplying together. Okay, so let's try another one. The next one we have, let me put this one on the side. The next one we have is trying to find the integral of t squared times et dt. Here we have a polynomial and the exponential. We know that exponential is going to be our last option to choose for u because the derivative of the exponential is always itself. The integration of the exponential is also itself. So it's pretty much like we cannot really do anything to simplify the problem. So let u equal to t squared, then du is equal to 2t dx. Let dv equals to e to the t dt. Then according to the antiderivative of exponential, v is just et. So let's do the integration by part, which is uv t squared et minus the integration of v du 2 t et dx dt, supposed to be t. Now we need to integrate it or simplify it first. Move out the 2, t et dt. T et dt is not something too easy to do it. So we have to do the integration by part twice. And it's actually really common for the integration by part. Like you can do integration by part multiple times. It's just more like this is just a technique. The goal is to break down a very complex one, hard to integrate, to something easier to integrate. So next we're going to do the integration by part for this piece. So I'm going to let u equals to t, du is equal to dt. I'm going to let dv equal to et dt, then v is equal to et. So let me copy the rest, t squared et minus 2. I'm going to do u times v, t minus the integration of the v du et dt, which we know et dt, the integration of et dt, this is going to be change back to just et by itself. You can leave your answer like that, or you can simplify it by writing it or multiplying the two. T squared et minus 2t et minus 2et plus c. So either this one or this one is your final answer. So here we use the integration by part twice. And it is common that some problem you're having to do it 3 times. But normally it's not going to be common if you're going to do integration by part 4 times or 5 times. Okay. Now let's looking at another example. Let me just erase this one for a second. And this one for a second too. So we want to find the integration of e to the x power times sine of x dx. So we have exponential and then we have sine function. So according to our trick, let u be the sine functions, or the trig function, sine of x. Then du is equals to cosine of x dx. dv equals to e to the x dx. Then v is going to be e to the x. Now, let's using the u times v, ex sine of x minus the integration of v du. So ex cosine of x dx. Integration of ex cosine of x dx. This is not easier than the original one. So did I do something wrong? In fact, we didn't do anything wrong. It's just a how to say that? It's just a different type of problem. So for this one, we're going to keep doing the integration by parts again the second time. But this time we're going to do just this part. So we're going to let u equals to cosine of x. Then du is equals to negative sine of x dx. dv equals to e to the x dx. V is equal to e to the x. Then what we have is going to be copied on the first part minus uv ex cosine of x minus the integral of negative ex sine of x dx. So it is safe for me to move the negative sign to the front and change it to plus. But I think I mentioned that it is going to be supposed to be easier, but we still end up with something kind of back into a loop. This is not easy to integrate, but because both e to the x power and then the trig functions, they are kind of, once you're taking the derivatives, they're not really changing too much. So what we can do is, instead of just looking at the one we just integrated, let's keep the original problem in the loop. Yes, this is a calculus class, but we're still using our algebra skills. So before I continue, I'm going to clean up the parentheses. So because of the negative, it changed back to minus again. So this is still, like, we still use a lot of algebra techniques here. So what we need to do here is we're going to treating them, instead of like integrations, we're going to treat them as algebras. I have two terms. They look exactly the same. Integral e to the x sine of x dx, integral e to the x sine of x dx. Can I adding them together? In particularly moving one to the other side? The answer is yes. We can move one to the other side. So we end up with 2 integral e to the x sine of x dx equal to e to the x sine of x minus e to the x cosine of x. And we're only solving for one. We're just treating them as, algebras. So we can divide it by 2. So we ended up with integral e to the x sine of x dx is equal to 1/2 e to the x sine of x minus 1/2 e to the x cosine of x. Or if you wanted to make it prettier, 1/2 e to the x multiplying by sine of x minus cosine of x plus c. Either way will work. So this is why I said this is another type of example. Because of the functions we have, e to the x and then the sine of x, when you're taking the derivatives, is more like going to loops. Like e to the x, whether you're taking the derivative or integration, it will not change. For the tricks one, sine and cosine, it's not going to change too much. The only difference is going to be the signs difference. Like the derivative of the sine is cosine, the derivative of cosine is negative sine, and then you kind of repeat it back and forth. So because of that kind of characteristics, we cannot really solving solving the antiderivative using the antiderivative way, but instead we can solving them using algebra way, and that is how we do it here. Okay, I think this video is long enough, so let me have another part of another video for more examples.